In this stress check tutorial, we will discuss how to import a complex 3D CAD geometry, auto-mesh with solid tetra elements, assign materials, loads, and constraints, compute multiple solutions by increasing the polynomial order of the elements on a single mesh, and perform advanced post-processing to assess convergence of stresses as the degrees of freedom are increased. The problem at hand is a drag brace geometry with forward, which are the smaller hull surfaces, loaded by bearing stresses, and aft, which are the larger hull surfaces, fixed. The material is aluminum, and we are interested in the critical stress value and location, and its local influence via gradient assessment. First, we will start a new session of stress check and import the CAD geometry by clicking the Import button. Select the parasolid file dragbrace.x_t and open. StressCheck's native CAD modeling kernel is parasolid, so parasolid files are preferred. The CAD geometry will appear with a 3D solid showing up as a maroon color. This geometry represents a drag brace, which could be part of an aircraft landing gear assembly. We will next go to the Geometry tab in the Model Input window and create coordinate systems in the drag brace holes. These will be used later for bearing load assignments. We will use the Action Object Method, or AOM, combos to select Create Point Offset, activate Off 1, and then activate the repeat box and enter 3. Note the GUI will update depending on the current AOM combo text. We want to create the first point at a 0 offset on the curves and increment by 0.25, as the parasolid range for trimmed curves is between 0 and 1. So we'll enter 0 for off 1 and 0.25 for the plus value. When we left-click on one of the whole curves, the 3 points will automatically be created, spaced 1/4 of the curve apart. We will do this for a curve on the other bore as well. We need a point in the center of each hole to represent our coordinate system locations, so we can change the AOM combos to Create Point Midpoint, and then click on 2 points spaced 180 degrees apart on one of the curves. The point will automatically appear in the middle. Repeat for the other hole as well. Finally, change the AOM combos to Create System 3-Point Plane. Click on the point in the center of the hole, then 2 other points to orient the system. The system will be automatically created at the first point with the z-axis parallel to the hole. Repeat for the other hole as well. We will use these later for loading. We will now generate a mesh of solid tetra elements by creating a global mesh record and using the Auto Mesh button. Records contain references to model objects or assignments and will appear in a long drop-down under the AOM combos for future access. Go to the Mesh tab and change the AOM combos to Create Mesh Auto to define a global mesh record. Select the drag brace and toggle the ratio, d/h, minimum length, and transition rate checkboxes. Enabling the ISO checkbox ensures that the elements have at least second-order curvature to better represent the underlying geometry. Enter 0.25 for ratio, 0.1 for d/h, 0.01 for minimum length, and 0.05 for transition rate. Click Accept to add the global mesh record to the long drop-down, and then click the Auto Mesh button to generate the mesh. This will result in automatic generation of about 16,000 solid tetra elements. This represents a fairly refined model in stress check. If we want to update the mesh record or any other record, we can select the record from the list, update the values, and click the Replace button. To delete a record, select the record from the list and click the Delete button. We will now define and assign linear isotropic material properties to the elements. Go to the Material tab, define Subtab, and click the Browse button. Select 2014 T6 aluminum from the list and close the list. Click Accept to add the material definition. For linear isotropic materials, we require a material name, which is the ID, elastic modulus, which is E, and the Poisson's ratio, which is nu. Go to the Assign subtab and make sure the AOM combos are set to Select All Elements. The ID combo shows 2014 T6 as that is the only available material definition. Change the color to aluminum and click Accept. The mesh color should be modified from pink to aluminum color to indicate the elements were assigned the materials. We will next assign the boundary conditions for this model, starting with the bearing loads in each of the smaller hull surfaces. We'll use the coordinate systems we created for the assignments. Go to the Load tab and change the AOM combos to Select Any Surface Bearing and make sure only the surfaces are displayed in the model by toggling the display objects to surfaces only. It is good practice to assign boundary conditions to geometry instead of mesh. Enter bearing for the load case ID, mag.dir for direction, which is magnitude and direction. Activate the System Picker button and select the nearest coordinate system. System 1 should fill in the system combo box. Select the nearest whole surface, enter a magnitude of 1,000 pound force, an angle of 45 degrees with respect to the system's x-axis, and click Accept. A load record will be added to the list. View the bearing load case arrows by checking the Load ID box. The bearing load will appear as a continuous sinusoidal traction distribution to represent our applied stress. In 3D elasticity, stresses or tractions, and not point loads, should be applied. Point loads cause singularities and will contribute to idealization or modeling errors. Repeat for the other hole, except use the system picker to select that hole's system, which will be system 2, and a magnitude of 2,000 pound force. We can use the same load ID to include both load records in the same case. If we want a new load case, we have to use a new load case ID. Let's check the bearing load case by changing the AOM combos to Check All Elements and clicking the Accept button. The sum of forces and moments from the bearing loads will be returned. If we want to use a different coordinate system for the load check, we can use the system picker or combo box to select it and click Accept again. Next, let's go to the Constraint tab to assign fixed constraints to the larger holes so they cannot move. Change the AOM combos to Select Any Surface Built In. Enter Fixed for the constraint case ID. Hold Shift and pick the hole surfaces. Click Accept and then view the fixed constraint case by checking the Constraint ID box on. Display elements only, since we no longer need to display the surfaces. We now have all the necessary boundary conditions for the model and are ready to set up the Solution ID. We will use the Solution ID tab to pair the Load Case ID and the Constraint Case ID so the solver knows what to solve. Enter SOL as the Solution ID, click on the Load Case ID and then the Constraint Case ID, and Accept. We are now ready to solve. StressCheck supports easy solution verification and mesh independence by allowing users to seamlessly increase the polynomial order of elements for one mesh, instead of iteratively refining the mesh over and over. After 3 increasing polynomial orders, we can assess convergence of any value in the model by seeing if the value is independent of polynomial order or degrees of freedom. For this analysis, we will start the polynomial order at 3 and increase all the elements to an order of 5 using a P extension. Let's go to the Solver window, Linear tab, and enter 3 and 5 for the P limits. Then go to the Solve tab and click the Solve button. The solution by a P extension takes a few minutes for this model. Once the solution is completed, there will be a % error that appears in the solver. This represents the estimated relative error in the energy norm, or more simply the global error, based on the total potential energy as the polynomial orders are increased. A value of 0.89% global error for a detailed 3D CAD is a good initial indicator that there were no modeling errors, such as cracks or improper boundary conditions. The global error is estimated because once we have 3 solutions, we can estimate the total potential energy of the system assuming an algebraic rate of convergence, and use this estimation of total potential energy to compute a relative error. More information on estimating global errors is available in the Master Guide under Theoretical Background. To study the relative error of the total potential energy in detail, we will go to the Results window Error tab. Make sure the AOM combos are set to Select All Elements. Set the solution to SOL and run 1 to 3. Click Accept and a graph window appears to show a plot of the global error with respect to degrees of freedom for the 3 solutions. As the degrees of freedom are increased by P extension, the global error should always decrease. How fast it decreases depends on the convergence rate. The ideal convergence rate is 1 or above, which is common for smooth problems with few jumps and stresses. We're at 0.93, which is reasonable for a complex 3D CAD model with many features causing high stress gradients. Also, 0.89% error is acceptable for a complex 3D CAD model. StressCheck will converge at a rate of at least twice as fast compared to other FEA codes. This makes it extremely efficient when solution quality is important. StressCheck post-processes on the fly, so it is not necessary to plan ahead what data you will be interested in or what locations in the model you will want to examine. This flexibility is one important advantage StressCheck has over other FEA programs, the ability to compute any engineering quantity at any time at any location in the model. This includes plotting stress fringes in the Plot tab, extracting maximum stress values in locations in the Min-Max tab, and capturing stress gradients of any resolution in the Points tab. We'll first go to the Results window, Plot tab, to plot the deformed shape in the fringe of the first principle stresses. Make sure the AOM combos are set to Select All Elements, set the solution to SOL and the run number to 3, the one with 1.1 million degrees of freedom. Activate the Fringe button and change the shape to Deform. Set the function to S1 for first principle stress, and set the midsides to 10, which is a fairly high resolution grid for plotting. Click Plot, and the fringes and deformed shape will draw. The deformed shape looks consistent with our assignments. The maximum first principle stress is about 275 KSI and is localized to a small blend between the small holes. This is a very high stress gradient near the maximum first principle stress, and therefore required sufficient mesh refinement and polynomial orders to represent. There are jumps between elements indicating discretization error, but we will still determine if the maximum converges before making any refinements. Click Display Reset to clear the fringes. By default, there is no averaging across elements or blending. To determine how much averaging affects the fringes, it can be activated by clicking the Average button and then Plot. The maximum should not vary much. It does not here. We can also plot the first principle stress fringe on just the element faces in the blend if we don't want to plot the entire model fringes. Set the AOM combos to Select Face Surface, set the tolerance to 2 degrees, and select any element face on the blend. All element faces in the blend should be highlighted. Click Plot to show fringes on just those faces. Then click Display Reset to clear the fringes. To check convergence of the maximum first principle stress in the blend, we will go to the Min-Max tab. Set the run to 1 to 3, the function to S1, and the midsides to 10. Activate the Locate Max and Maximum buttons. Locate Max will create a point at the maximum first principle stress location. Pick the same element face as before to select all the blend faces and click Accept. A graph window appears containing the maximum first principle stress value and location for every run, an estimated maximum limit, and an error. Based on the trend of the 3 maximum first principle stress values as the polynomial orders increased, the estimated error in maximum first principle stress was calculated to be 1.03%. This is acceptable, so refinement won't be required. In the Points tab, StressCheck has the capability to compute any engineering quantity anywhere in the model with any resolution. This means we can define geometry for advanced post-processing and extract high-quality gradients along curves for our stress analysis reports. We will extract a gradient of first principle stresses through the location of the maximum first principle stress value using a surface curve. Display the points in the curves. Go to the Model Input window, Geometry tab. Change the AOM combos to Create Point Projection. Pick the point at the maximum first principle stress location, hold Ctrl-Shift, and pick the 2 vertical curves of the blend. Click Accept. 2 points will automatically be created. Next, change the Surface Curve selector to Curve and change the AOM combos to Create Surface Curve 2 points. Display the surfaces. Click the Blend surface and the 2 points we had just created. A surface curve will automatically be created through the maximum stress location and on the blend. Go to the Results window, Points tab, and change the AOM combos to Select Any Boundary selection. Set the solution to SOL, the run 3 to 3, the function to S1, the number of points to 30, and activate the Display Points button. Display the curves only now. Pick the surface curve, and then click Accept. A graph window appears with a first principle stress gradient on the curve. We can easily see how the stress changes across the blend radius without interpolation or extrapolation. StressCheck does not require extractions to be limited to element faces, edges, or nodes. As long as the extraction is somewhere within the mesh, the user can be creative with his or her post-processing. For more information on StressCheck's features and theoretical basis, please consult the Master Guide.